Hello, everyone. So I'm gonna talk about the today's notes. This is for Friday, April 3rd. And this is where we start. This is the page 258. You've already done the previous clicker questions, and hopefully you checked the summary at the top. Now we are going to start from the example problem, example number 24, okay, on this page. So the problem is 5 kilogram mass is suspended vertically by a spring with a constant, this should be lowercase k, 400 newtons per meters. Initially, the mass is at rest and the spring is not compressed. The mass is held by a restraining string whose length matches the relaxed length of the spring. And the spring is then compressed 0.2 meters by an external applied force and held in that position. And those are shown on the figure. First, left side is the initial case and the right side is the after we compress it by 0.2 meters with F. So we will find the work done by the external force F. Okay, so we're looking for WF sub F. So again, what is given is mass hanging from a spring, and we're trying to find the work of applied force, external force, and the assumptions. Again, you can make several assumptions, but this is now we are in energy conservation, so we do work on the energy terms. So you can mention, like, when you get rid of some stuff, you can write them here if you like. Those are the examples here. So no temperature or pressure change and no heat transfer. Those are so far kind of our default things, which will change soon, but we can write it right now. And the plan is, again, using conservation of energy. We will find out the work done by F. You may think you can use the work term to find out the work done by the external force, but F is not given. And also we are going to investigate that, but is it a constant force? We will think about that after we draw our free body diagram. So if F was known, then maybe it would be just straightforward, and then F dot D if it is constant. If not, you integral if the function was given, and so forth. But conservation of energy is a way to go for this problem. Okay, in estimation, so what we are doing with this F is we are lifting up the object, right? But not just that. So you're not just lifting up the object, lifting up the object, and if you do that, you are using the work done by F as the to kind of do this against the potential energy, gravitational potential energy, first of all, because there's an elevation. So you need to kind of cover that up with the work done by F. And that would be, again, simply, as it says here, energy just to raise 0.2 meters is about 10 joules. Right? It's like mgh, mgy. But that work done by F doesn't really do that only. It also compresses the spring. That means we should get more than 10 joules. Okay, so that's a good estimation. And so next we will solve the problem. First we draw a free body diagram. And so what we have is we have spring force. So you can show that downward because we are compressing it upward. So spring force is going to be opposite to the compression. And there is weight force downward and also the applied force F upward. And so again, you may think that using work definition might be a way to go. First of all, we are not sure if it's a constant force. And if it was constant, then you could use F dot D, but we don't know F. Then that means we can't really use this equation. And also, F shouldn't be a constant force because you know that Fs is variable. Although weight force is constant, with the compression changes, X or Y in this case, it's vertical, it changes, F will take different values. So it's also a variable force, and we have no idea what it is. So instead, we will be using conservation of energy. Okay, so again, we write the equation, split up delta U terms for gravitational and elastic potential. And then we think about how to simplify the equation. So we have delta K. Do we have change in speed, or what are the speeds in the beginning and at the end? Okay, it was stationary and it is stationary at the end as well, so that's why it goes to 0. And so we're kind of like taking note of those, like why they are 0. Either you can list them underneath this equation, or you can write it next to the 0 that when you cross it out. Either way is fine, but make sure to explain why. Okay, this is really the best way to learn this material. And as usual, we are going to take delta I and Q to 0, and we already mentioned why in the assumption here, so I just want to highlight that. Oh, not that one. No temperature or pressure change, and also no heat transfer. That's why they will go to 0. And there is a change in elevation, so we're going to keep the delta UG term, and there is a spring being compressed, so we will keep that term as well. For the work term, we are going to look into the forces we have in the free body diagram, and spring force is already accounted for in the elastic potential energy. So instead of writing work done by the spring force, we choose to keep the energy term change in elastic potential. Weight force is also accounted in the change in gravitational potential. Okay, so those terms are going to go to 0. That means the only work term we have is the work done by the external force F. Okay, so if we solve the left side, that is our answer because we are looking for the work done by that force. What we do next is we simplify this energy equation, and then we are going to expand the parts. This is delta UG, this is delta UE, and we have work term on the other side. Again, it's always final minus initial. And next we are going to do more simplifications. Initially, as we have it in the figure, so this is an important detail and you should also have this. Y0 is 0, and we said that y is upward. So you can also put this right here and not say that if you like. But we need to show that, okay, where we choose to be the potential energy, gravitational potential energy 0. And we have that there, and that's our initial position or initial case. That means this UGI goes to 0, and we have it on the right side as well, as we've shown here. And the next, at the relaxed position, we do not have the spring force either. That's why UEI is also 0. Once you make those simplifications, you get total work done, which is just by the external force, it being UGF plus UEF. Okay, so we just need to find those to figure out what the total work done is. So the work done by the force F, external force F, does two things then, right? It raises the gravitational potential energy of the object. That's what UGF is. And it also raises the elastic potential energy of the object. And the object has more energy at its finish point than it did at the start, rather than the same amount, okay? And when we plug these in, what is UG? UG is mgy, and UE is 1/2 kx squared. Put these in there, and then it turns out y final and x are the same because the elevation is the same as compression in this problem. So although they look like they're two different things in the equation, symbolically, they are the same. So we're going to look into the figures to figure that out. And we're just plugging numbers in. As you can see, little k is the spring constant, that is 400 newtons per meters. And this is what we're getting in terms of newtons meters. And we know that Newton meters is joules. That's the energy term or the work term. And this is our final answer. Okay, so that's our answer. We boxed it. And that is how you solve for the work done by the F. Okay, since that's the only work term, that's what we get. And as we expected, it is more than 10 joules. And if we needed the value of F, we could still like find it from free body diagram, but since F is a variable, maybe they would ask you to find it when the spring is fully compressed. Then you need to apply Newton's second law and find out, for that case, find out what is the spring force, what is the weight force, and then you can find the external force as well, so that the system is in balance because it's not moving at all. That means it doesn't have an acceleration when it is fully compressed. But other thing that I want to talk about here is, if you look at the initial case, what is the force on the, what is the amount of force on the restraining string? What do you think? Okay, think about it. There shouldn't be any, right? So it looks like there's a string, there might be tension, but we don't need that. It's just for the safety, but it's already at the relaxed position. That means spring is already stretched as much. And what is F then initially? F is also 0. Like the tension should be 0, because what happens initially is at y is equal to 0, weight force balances out with the spring force. Okay, those two are equal to each other. But then when you move the object a little bit with F, you are building more force because, again, spring force is changing. So that's, I think, a good point that you could also note it in the discussions. It doesn't mention here. Okay, so hopefully now in this problem, you can see that the energy deposit came from the work input by the force F.